Have you ever encountered an exponent that looks like a fraction? Fractional exponents might seem intimidating at first, but they are simply a compact way to express both powers and roots simultaneously. Let's break down the logic behind these expressions. In science and engineering, fractional exponents help us model everything from how sound travels to how biological organisms scale. Understanding them allows us to navigate complex dimensions and solve for unknown variables in nonlinear systems. The fundamental rule is simple: the numerator represents the power, while the denominator represents the root. This means x raised to the m over n is equal to the nth root of x raised to the mth power. You can solve these in two ways: either square the base first then take the root, or take the root first then apply the power. Usually, taking the root first keeps the numbers smaller and easier to manage mentally. This works because of the power of a power law. When you raise a power to another power, you multiply them. Since a root is the inverse of a power, a fractional exponent perfectly represents that reciprocal relationship. On a graph, fractional exponents between 0 and 1 create curves that increase at a decreasing rate. For example, the square root of x, or x to the 1/2, is the upper half of a sideways parabola. When we graph y equals x to the 2/3, we see a unique cusp shape. Because the numerator is even, negative x values result in positive y values, creating a symmetric graph across the y-axis. Let's solve 27 to the 4/3 power. First, find the cube root of 27, which is 3. Then, raise that result to the 4th power. 3 times 3 is 9, times 3 is 27, times 3 is 81. What about negative bases? If the denominator is odd, like the cube root of -8, the answer is a real number, -2. However, even roots of negative numbers require imaginary units. When dealing with variables, distribute the fractional exponent to every term inside the parentheses by multiplying. 6 times 1/3 becomes 2, and 3 times 1/3 becomes 1, simplifying our expression significantly. To graph y equals x to the 3/2, we calculate points. At x equals 4, the square root is 2, and 2 cubed is 8. This curve grows faster than a linear function because the exponent is greater than 1. All standard exponent rules still apply. When multiplying like bases, add the fractional exponents. This often requires finding a common denominator, just like basic fraction addition. Similarly, when dividing, you subtract the exponents. 3/4 minus 1/4 leaves us with 2/4, which simplifies to 1/2. Our final answer is simply the square root of x. To recap, the denominator is your root, and the numerator is your power. You can apply these in any order, and all the laws of exponents you already know still apply to these fractions. Visually, exponents between 0 and 1 create concave curves, while exponents greater than 1 create convex curves. This visual intuition helps you verify if your calculated coordinates make sense on a graph. Let's test your knowledge. Try simplifying 16x to the 4th, all raised to the 3/4 power. Break it into parts, calculate the constant first, then apply the power law to the variable. The 4th root of 16 is 2, and 2 cubed is 8. For the variable, 4 times 3/4 is 3. The final simplified result is 8x cubed. Great job mastering fractional exponents. Generated by Vision Solve AI.